Welcome back. This is episode 3 of Binomial Coefficients. Today we're going to find a simple formula for them. So, start with an example. In how many ways can you arrange 4 people in a line? Well, let's say our people are A, B, C, D. I guess this is an ordering in itself, right? Let's say that A here is first, and D here is last, right? Let me just order them like this. That's one ordering. We can do A, C, B, D, but we're going to be here a while. There's actually quite a few of these. Even for 4 people, this number is quite big. So we want to get a better mathematical approach to figuring this kind of question out. Well, okay. The number of ways we can arrange 4 people in a line. Let's break up our problem. So the number of ways, let's say ways to arrange 4 people. Well, we can choose our people one at a time. So it's the number of ways to choose who goes first, right? We can choose who goes first times the number of ways to choose, I'll just kind of put this quotes here, who goes second, right? Choose who goes second, times the number of ways to go third, times the number of ways to go fourth. Okay. So how many ways can we choose who goes first? Well, we have 4 choices, right? A can come first, B can come first, C can come first, D can come first. You might think that it's just 4 all around here, but this actually isn't quite true. If we have chosen A, for example, to go first, like in here, for example, well, then A can't go second, right? However, B or C or D can all go second. So there are 3 ways to choose who comes next. Similarly, if we have our third one to choose, for example, here we've chosen A and C already, then either A or C can't go third, so we have to choose between B and D. So we have 2 choices left. And then finally, once we've chosen all 3, let's say in this case when we've chosen A, C, and B, then we actually only have 1 choice left, right? It has to be D who goes last, right? So it's 4 times 3 times 2 times 1. And you may have seen this notation before for this kind of number. This is called 4 factorial and is written like this with this exclamation point. So this is written, you can read this as 4 factorial. If you're wondering what this is literally just what I've written up here, right? So in general, if we have n factorial, or n is some integer, this is just n times n minus 1 times n minus 2, yada yada, down to 1, right? Okay, so I think this definitely suggests something, that maybe the number of ways to arrange n people in a line could be n factorial, and yeah, that is true. So let's get into the first proposition that we have today. The number of ways to permute n objects is n factorial. So what is this word permute? Permute just means order, right? You can think of this as just saying how many ways can you order n things, or order n people in a line. And the proof is pretty much exactly what the example is, right? So the number of ways to permute n objects, right, or order them, we can just say, okay, this is the number of ways to choose who goes first times blah, 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 times the number of ways to choose who goes last, right? We just choose them one at a time. The number of ways to choose who goes first, there's n choices. The number of ways to choose who goes second, there's n minus 1 choices. And then there's n minus 2, and so on, down to 1, because to choose who goes last, we only have 1 choice left, right? And so this is n factorial. Okay, pretty simple. In a way, you can honestly say that really the defining feature of n factorial is this property, right? Even more important than its multiplicative definition here, it's that n factorial is the number of ways to permute n objects. This is really the most important thing about n factorial. Okay, great. This one looks a little more complicated. I'm claiming here that the number of ways to permute n objects is also equal to this. It's equal to n choose k, n minus k factorial times k factorial. Okay, this one takes a little bit more work to do. What it comes down to essentially is that, by the way, k here is anything from 0, 1, up to n, right? So it's true for any k. It doesn't matter what k you choose. This is true. Okay. So I want you to imagine that we essentially fixed some k here. I want to find out how can we permute these n objects. So let me just write this down. Number of ways to permute n objects. So in a way, what we did in the previous example is we took it step by step. We saw who went first, who went second, and so on. Well, here I'm going to break it up in a slightly more general way. This is the number of ways to choose the first k objects. Okay, first of all, you choose the first k. Okay, you can imagine you have a line of n people. You choose the first k people to go in the line. Times, okay, so we've chosen k to go first, times the number of ways to order or permute, right? Permute. To permute the first k, because remember we've chosen the first k, but within those k, they can be in any order. So we still have to choose which order they're in. And similarly, all the people who aren't those k, the remaining n minus k, also have to be ordered. So this is times the number of ways to order the last n minus k, right? You can imagine sort of you have some kind of line of people, for example, right? For example, we have, let's draw a bit of a picture here. We have some amount of people, right? Some n people. And if we want to order them, what I'm essentially saying here is you can choose k of them to go first. So let's say you kind of put them in two camps. So we have, these don't necessarily have two, they can have more than two. You have the k first people in the line, and the n minus k last people, right? So our first step, right, essentially this step right here, is to sort these people into these two different groups, these two different camps, right? And then from there, we can order them, right? We order the first k, and then we order the n minus k others. So, from here, we actually put them in a line, right? We order the first k of them, and then we order the n minus k others. And so this is just equivalent to just permuting them, right? The end result of this complicated process is just that we get a line of n people as we want, right? So I'm being a little bit vague on the details here, but essentially, for any k that you have between 0 and n, this process counts the number of ways to permute n objects, right? The number of lines of n people that you can make. It's the same thing. But now, what are these things, right? What is the number of ways to choose the first k objects? Well, this is really just, right, choose a k element subset of the n objects, right? Kind of think of it here, you're just choosing which of these k you want to go first, right? Choose k of them to go first. Choose a k element subset of the n object. So what is this? This is just n choose k, right? This is what we've been working. What about the number of ways to order the first k people? Well, this is just the previous proposition, right? we said the number of ways to order n things is n factorial. So the number of ways to order the first k things is just k factorial, right? Once they're in this little camp here, this little group of people, we just order them, and there's k factorial ways to do that because there's k of them. And similarly here, when we're ordering these n minus k people, well, there's n minus k of them, so there's n minus k factorial ways to order them. So this kind of gives you a flavor for a lot of these proofs in combinatorics, which is like the field of math that this is under. A whole lot of this sort of counting business, right? You're trying to sometimes count things in two different ways. Okay. But now we've secretly done something. We've actually secretly found a formula for n choose k, seemingly out of nowhere. And I call this a corollary because the proof is pretty much immediate, right? What is the number of ways to permute n objects? Well, on the one hand, it's equal to n choose k, k factorial, n minus k factorial by proposition 2. By proposition 1, this is just n factorial. And now just rearrange, right? N choose k must then be equal to n factorial over k factorial n minus k factorial. Nice and easy. So this is, I think, a pretty striking result. It's maybe not so obvious at first when we define these binomial coefficients that we can actually find a simple formula for them. Well, you can argue this is not such a simple formula, but there's worse formulas in math. So there you go. You have an actual formula for n choose k. A lot of people actually start by defining them this way. I've kind of made a point to not introduce this so early because I think their properties in terms of counting the number of k element subsets of an n element set, and also their connection to Pascal's triangle, is more important than this meaning of them, right? But some people like starting with this meaning. This is, of course, a very useful thing, and well, we'll see how it's useful, mainly in terms of computing these numbers, right? So 5 choose 3. This is our favorite example, right? I've talked about it in episode 1 a few times. So we found a combinatorial way to show this. We can see this in Pascal's triangle as well. But we can just do a pretty simple calculation right now to just find what this is, right? Using our new formula. So maybe I'll just remind ourselves of our formula here. So n choose k is equal to n factorial over k factorial n minus k factorial. It's a bit of a scary looking formula, but I think after using it enough, we'll get used to it. Okay, so 5 choose 3. Right? Just plug it in and see what happens. So we have 5 factorial on top, then we have 3 factorial, and then 5 minus 3 factorial, which is just 5 factorial over 3 factorial 2 factorial. Okay, here it might just be easiest to just write this out to just see what this is. 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 times 1. And now we can cancel some of these, right? So these 3 cancel out. And we're left with 5 times 4 over 2 times 1. 5 times 4 is 20. 2 times 1 is 2. And we're left with 10. And this is what we found in episode 1 as well. But I hope you'll agree that this is a much simpler way of finding what 5 choose 3 is. Okay, 4 choose 2. Again, mostly straightforward. 4 choose 2. 4 factorial over 2 factorial. 4 minus 2 is just 2, so 2 factorial. Okay. Now, again, we can kind of write this out. I think you'll notice here that there's sort of a pattern in how we can do these, where we can always cancel out something, right? We always cancel out these first terms that show up. I'm left with 4 times 3 over 2 times 1. So 4 times 3 is 12. 2 times 1 is 2. So 6. And again, this is what we found in episode 1. This is perhaps a simpler one where you wouldn't need to go through this formula. But there's something like this where, yeah, you probably want a formula for this one. This one's a bit tougher to try. And let's just see what it is. So 10 choose 7 is 10 factorial over 7 factorial, 3 factorial, because 3 is 10 minus 7. And here it would be helpful, instead of writing out every single term, to kind of take a bit of a shortcut here. You can notice that 10 factorial is just equal to 10 times 9 times 8 times, well, 7 times 6 times 5 times 4, but really this is just 7 factorial, right? And this is over 7 factorial times 3 factorial is just 3 times 2 times 1. Okay, so 7 factorials cancel. Again, we always get something that cancels in this kind of situation. And now we're left with, well, this mess. It's not exactly the most fun thing to work with, but okay. Maybe we can do some simplifying. I see here it would be helpful maybe to put this as an 80 times 9 over 3 times 2. I'm going to leave that as a 2 times 3 because now we can do some canceling, right? 80 over 2 is 40. 9 over 3 is 3. And so we're left with 120. Okay. So this is a very useful formula. Again, I want to reinforce that I think this formula is not the defining characteristic of binomial coefficients, but it is very useful to have, and it really kind of grounds these numbers in a way that we can really easily compute, especially for large binomial coefficients, right? Something like 10 choose 7. This would take a while to write out with Pascal's triangle, and would be even worse if you're trying to list out all the sets, right? So this is a much quicker way to do this. Okay, perfect. Thank you for watching. I'll see you in the next episode.